All right, so let's get started with today's class. Hello everyone, welcome again to our machine learning career track. For those who are watching this recorded and for folks who are joining in live as well, my name is Mihir Thakkar and I'm the founder and instructor at Code Heroku. We are in the fourth module in our machine learning career track right now, which is on deep learning. In our today's class, we'll be covering convolution neural networks. We'll see what kind of neural networks exist out there, and we'll also see one specific types of neural networks, which are called convolution neural networks, which are specifically used for image data. I mean, there are some other applications, but most likely in the field of computer vision, in the field of image recognition, object detection, you will see people talk a lot about convolution neural networks. And these are the state-of-the-art networks that exist today. So any image recognition task that you might have heard of, it's most likely that they are using a convolution neural networks behind the scenes. So we'll see the mechanics of how these things work, and we'll also implement them in Python, of course, right? Because that's how our course is laid out. We want to make sure that we cover the theory as well as the practical hands-on session. So we'll use TensorFlow and Keras API to implement the convolution neural networks and solve some real challenges. All right. So let's see what we are going to do today. We, of course, want to give you a quick recap. There has been some break on things that we have covered until now. So I want to make sure that things are fresh in your head. So we'll do a quick recap of whatever we have covered until now in deep learning module. Then we'll see some neural network architectures. I'm not sure we'll be able to touch a lot on the architectures today, but we'll see if we can now cover a bit of the different kind of architectures that exist. Then we'll see a bit about deep learning for computer vision and how you could use deep learning for image data. And one specific application or one way to do this is using convolution neural networks. So as our class title suggests, our today's discussion will be mostly focused around how to use convolution neural networks for image processing, not image processing, but computer vision and object recognition tasks. And of course, then we'll move on to our hands-on exercise. This time, but we will use a tool called Google Colab, which is the Google version of Azure Notebooks that we have been working until now, right? So Microsoft's version is Azure Notebooks. Google has their cloud-hosted Jupyter Notebooks, which they call Google Colab, which is similar to a notebook, but it's a different interface. All right, and one of the reasons that we'll be using Google Colab today is to use the GPUs that they provide. So within Google Colab, you could use GPUs and TPUs. Within the cloud without having to worry about parallelizing your code, and Google will do those things for you, and just you'll get speed ups of probably things that would take maybe 1 hour on your machine or on Azure Notebooks that would get completed within few minutes over there, right? So our learning training speeds when we want to do a lot of experimentations. Sudipto was pointing out last time that hey, there are so many hyperparameters that are involved when we are doing a deep learning, and of course there is a lot of experimentation involved in deep learning. And that's the reason we want to be able to use a tool that allows us to do that. Imagine if you are spending 1 or 2 hours just to train your model for each different kind of architecture or each different hyperparameter, it's very difficult, right? So that's why we'll be using Google Colab to use the GPUs that they provide in order to speed up our learning. All right, so let's see what we have seen until now, right? So let me get my pen over here. So this is a fully connected neural network that we have been working with until now. On the input side, we have some features over here. This is our feature vector X. And what we said is what universal approximation theorem told us is even with just one hidden unit over here, right? With one just hidden layer over here with some number of units, you can approximate as any input function that you give me. Right, so if you give me enough hidden units, if there are enough number of hidden units over here, I can approximate any function in this world, right? and that is powerful. That is powerful. The only problem that you need to think about is you need to be aware of is if you are not overfitting on your input data itself, and you are not just having so many parameters that you are just essentially remembering your entire input data set, right? Because the whole purpose of machine learning is not to remember your input data, but be able to generalize from that input data so that you can make predictions on your test data as well, right? Um, and we said that these input units are connected to these hidden layers through a set of weights, right? So we have W1 over here, and I said, so let's keep the terminologies consistent. So I had W11, W12, W13, and so on. And this entire input vector, I was calling it as W1, right? If you recall this, the set of weights from the input layer to the hidden layer, we were calling it W1, which was the input weight vector, right? If you put that in a matrix form, it's a vector then, right? If you put all these parameters in one line over here. Similarly, you would have some weights from the hidden layer to the output layer, because we said that these strengths are not equal, right? That's how we are trying to model these things. We want to make sure that these strengths are not equal in strength, or maybe these connections are not equal in strength, and that's why we have some strengths from this hidden layer to this output layer as well. So maybe this is W21, W22, and W23, and this was the weight vector W2, right? And initially we start off with some random weights, right? You could initialize all the weights to 0, and then you make some prediction. In our case, we said that let's make a prediction y hat, which is from the forward path, right? So this input, when passed through all these weights, this was the forward path, you would get some prediction y hat. Now, obviously, because you have randomly initialized these weights, you would get some error in your prediction. So you would have some cost associated with it. You would have some cost associated with making this prediction, and now you could model this cost. There are different loss functions that you could think of. One simple loss function that we came up, or we used, was during our derivations, was the root mean square error, right? And essentially what you would do is, and how did we minimize this error? Can someone tell me the name of the algorithm that we had derived as well? So this was the forward path. We got some error, and based on the error, now we want to adjust these weights so that our error ultimately reduces. So what was this path? How did we adjust our weight to, what was the terminology over here? What did we do to reduce our weights? Not reduce our weights, but to adjust our weights such that we get the error reduces. So if we want to adjust our weights, right? So we want to say W1 equals to W1 plus delta W1, and W2 equals to W2 plus delta W2. So how did we come up with these delta W1 and delta W2? What was the name of algorithm? So which was the optimization algorithm that we used? First of all, tell me that. So which is I guess the only optimization algorithm that we have studied till now, which is widely used in machine learning? So guys, I hope you are able to hear me properly. And if there are any questions, please do let me know. My question to you is, which is the optimization algorithm that we have studied till now, which we use to adjust these weights? So have we learned something about the stochastic gradient descent, right? Did we use stochastic gradient descent to adjust the parameters? Yeah. And the concept, or the thing that we also studied was not only that you could adjust these W2 once, you could propagate this error backward to the hidden layer as well, right? And you could propagate this error over here, and this was called as back propagation algorithm, right? So we back propagated the error to adjust all the weights in our neural network. Do you recall that now? So this was the forward path where we make the predictions. And then we also did back propagation to adjust these weights. And we went through an elaborate derivations, if you could remember, on for the back propagation as well. All right. All right. So hopefully now everything is fresh in your head on what have we seen until now in terms of neural networks and specifically deep learning or deep neural networks. All right, so then we in our last class we also implemented, so we first started off with implementing neural networks from scratch, and we built our own neural network class. So once we understood the dynamics of how neural network works, we said that okay, this is good, but this is too much tedious, right? We can't be writing our own class every time we want to build a neural network. So we'll use a tool such as TensorFlow, and we'll be using the Keras API, which is also exposed through TensorFlow. So we know, if you recall, this is a screenshot from our code from last time in how we implemented a simple neural network like this one, which had 3 hidden units, 2 input features, right? So we had 2 input features, which was the student IQ and the score that, or the hours that, the IQ of a student and the hours that the student studied. And we had 3 hidden layers, 3 hidden units over here, 3 hidden units, and we just had 1 hidden layer. And based on that, we were trying to predict if the student will pass or a fail on an exam, right? So this is how we went about implementing this simple neural network using TensorFlow and Keras API. So there are 2 ways you could use the Keras API. You could either build sequential models, or you could use something called as functional models. Okay, so we don't want to go too much into the functional API as such, because for whatever we are going to do in the class in next few days, no, the sequential API is more than enough for us. So in the sequential API, we added a dense layer over here, which had 3 units. We said that the input shape has 2 input features in it, and we were using the ReLU activation function, right? We also discussed last time briefly about the exploding gradient and the vanishing gradient problem that neural networks go through. We said that if we initially people thought that it was a good idea to use sigmoid functions in the activation units over here. But soon people realized that it's not a good idea, because calculating the derivative of sigmoid over there is not so, and the exponential function itself is not so compute efficient. So instead we'll use a ReLU function, which made it more easier to compute, and as well as it got rid of the vanishing gradient problem. We still have the exploding gradient problem over here, but it's still better, right? So this was our hidden layer, and then we added a dense layer over here with 1 unit over here, because it was a binary classification problem, right? If you have more classes, you will have more nodes over here. If you have just 2 classes, you will have just 1 node, which is pass or a fail. And then we could compile the model using different loss functions. So over here, there are 2 options that I'm providing. One, you could use something called as a binary cross entropy loss, mean squared error loss, and there are different kind of optimizers which are available as well, right? So stochastic gradient descent algorithm that we have already studied, and there are other derived versions of stochastic gradient descent as well. Now there are modified versions. Now one which is called as ADAM, which is widely used again in deep learning. And here's the metrics that I want to print out, right, which is the accuracy. If you summarize the model, this is what the model looks like. And we also calculated the number of parameters last time, right? If you recall, now if this is input feature size is 2 and we have 3 units, so you have 2 times 3 connections, which is 6 connections. But we also have, where is this 9 coming from? Does anyone recall where is this 9 coming from? You have 2 times 3, which is 6, right? But we have 3 additional parameters. Where is that coming from? Yeah, Sudipta got it right. The W zeros, right? So you have the W zeros over here as well for each hidden unit over here, right? So this is 6 plus 3, which gave us 9 parameters to learn. And the output unit, again, you have these 3 connections, 1, 2, 3, and you have your bias term, which is 3 plus 1, which will give you 4 parameters. Okay, is this fresh now again? All right, so this is what we did, and now we compiled a model. And once you have your model built, it is pretty similar to scikit-learn API in terms of fitting the model and making the predictions, right? So you just say model.fit, you provide your X train, your Y train. The epochs are the number of times you want to run your stochastic gradient descent algorithm, and the batch size. If it's a mini batch gradient descent, so you could provide a batch size of like 1, 10, 20, 50, and so on, depending on the size of training data that you have, right? So if I have like 10,000 training points, maybe I would start off with like batch size of 20. If I have maybe 50,000 training points, 50 batch size of 50 is good as well. Okay. All right. So this is how we built and compiled our neural network last week with Keras API. So other thing that I wanted to revise was this bias variance trade-off. And the reason why I talk a lot about this, because the whole game of neural networks, if you think about, is in terms of balancing these two things. Even though when you talk about neural networks, there isn't the bias variance trade-off that generally people talk about in machine learning, because today we have been able to come up with techniques which don't compensate for one. Like if you are trying to compensate for variance, it won't affect the bias as such. So there isn't this concept of bias variance trade-off, but still these two things are important. Bias is not much of an issue in neural networks because given enough number of hidden units you put in, it's highly likely that you are gonna there are more chances that you're gonna overfit rather than you're gonna underfit, right? So given the compute capacity and the memory storage that we have today, if you have 1 million, 10 million parameters, and if you have it's highly likely that you're gonna overfit rather than you're gonna underfit, right? And that's the reason why I'm bringing this up a lot in terms of the whole game. And everything that you do in neural networks or in deep learning is to balance these two things. Because again, remember, the whole purpose of machine learning or any kind of learning in general is to come up with a generalized function. It is not to remember the input data. Over here, you're trying to remember the input data exactly, right? That's not the game. The game is to be able to model the input data in such a way that the future test data, the model works better on the test data as well, okay, on the data that you haven't seen before. So this is what generally a graph would look like in terms of, as the model complexity would go on increasing, your training loss would decrease, right? But after a point, you would see that this your validation loss or your test data loss will go on increasing. And the reason is you are not generalizing well, you are overfitting, right? And so you want to be into this sweet spot over here, which is the appropriate fit over here. Okay, does that make sense? So then I went on to the discussing on what kind of handles do we have in terms of controlling this, right? Because these things, if you look over here, if you recall, now what were the parameters? Where are the parameters of these models located? Can you tell me where are the parameters of the model? What are the parameters of this model? If I annotate this entire thing, this entire vector as W1, if this entire thing is W2, okay, and let's say we don't have bias. So what are the parameters of this model again? Can someone recall? What are the parameters of the model that we are actually trying to learn? After you do the model.fit, what are we actually learning? Go back to the first discussion that we had on linear regression. When I said, no, when I say that I'm doing machine learning, what am I actually learning over here? When I say y is mx plus d, right? And your m and the b are the parameters of your vector or your parameters of your model, right? So what am I actually learning over here? So not the trend as such, Sudipto. Now talk in terms of the parameters and the notations that we are using over here. Are we learning y? Are we learning m? Are we learning x? Or am I learning b? So Nitesh says we are learning y. So the output of, you think that when we say model.fit, this thing will return y? Is this y equals to model.fit? No, right? It is the m and the b, the parameters of the model, right? So the parameters of the model are the coefficients that we are trying to learn. So over here, the parameters of the model are W1 and W2 that we are actually learning. Correct? So given that we are learning the parameters of this model over here, how do we control? So these things are learned, right? These things are, is something that we are learning as part of our stochastic gradient descent algorithm or backpropagation algorithm. So how do we control where do we lie, right? The W1s, W2s, we don't have as such like proper control on them, right? We don't, we can't, like we have some control on how the W1s and W2s we arrive on. But stochastic gradient descent is essentially a trial and error method. So we don't control that. So how do we find out, or how do we make our networks such that we fall in this situation? How do we make our models fall in this situation over here that we are generalizing well, right? So the answer to that is by tuning the hyperparameters of the model, right? The answer to that is hyperparameters, which we actually control. The W1s and W2s we learn, but the hyperparameters of a model, we actually control them. It is something that you as a machine learning engineer, you set. And these are some examples of the hyperparameters that you have control on. So you could select the activation function to use, right? So you could select whether I want to use ReLU, whether I want to use a tanh function, whether I want to use a sigmoid function, right? And the parameters of that activation function you can control. You can also control the number of layers, right? And last time we had an elaborate discussion on how these things also affect the performance of your neural networks. As the number of layers increased, we saw that the number of hidden units would increase, and thus the number of parameters of your layers would increase. And you tend to overfit. If you have a lot of a lot of parameters and not enough data, right? So as your number of layers increase, you can shift towards more the right over here. So in my notations, or when I'm in my discussion going ahead, I'll be saying when I say going towards right, which means going towards overfitting. When I say go towards left, which means going towards underfitting. Okay, so keep that in mind when I say let's move towards right, which means let's move towards overfitting. So we'll be moving towards right when we increase the number of layers. If you increase the number of hidden units, again, it's the same thing. You increase the number of parameters. The learning rate over here, right? So if you decrease the learning rate, that means that you are trying to come up with this global minima. So this is how the neural network, the cost function associated with the neural network would look like. It's no, it's not a perfectly convex space, right? So you might get stuck in some local minima over here if you if your learning rate is too high, right? So if your learning rate is too high, you might get stuck over here. You might if your learning rate is too high, or no, if it is too low, you might get stuck over here. If it is too high, then you might just jump to different things, and you might have a exploding gradient problem over there. So you can control the learning rate and still come to a situation which you know you would want to ideally be in. You can control the batch size of the stochastic gradient descent algorithm on number of training points that you're giving to your algorithm at one time, and the number of epochs as well. Now you generally there is a technique which is called as early stopping, wherein you, instead of training your network through the entire epoch cycle, you would tend to stop the learning midway, so that you intentionally stop it such that you hope that during the test data you are not so hopefully that you are not overfitting, right? If you run your algorithm for 1 year, if you run your neural network training for 1 year for 10,000 epochs, then most likely you're going to overfit, right? So that's not what something you want to do. You want to train your network enough so that the error is less, the training error is less, but still you don't do poorly on the validation error as well. Now regularization is another technique that we have seen, specifically not to throw in just a few random words. There is a technique which is called L2 regularization as well. I mean, not random words, but no, I don't want to put in jargons over here because we haven't discussed a lot about L2 regularization. But with L2 regularization, essentially you're trying to make sure that your weights, the value of these weights are not too high, right? And hopefully if the weights are not too large, then you are not going to overfit. And there is another technique which is very new specifically for neural networks. All these apply to other machine learning techniques that we have seen so far as well. But dropout is something unique to neural networks that I want to discuss slightly, because we haven't spoken a lot about dropouts. So here's what people do in dropout, here's how you can avoid overfitting. And as I said, neural networks are prone to overfitting. So here's one strategy on how to avoid overfitting using a technique called as dropout. So this is what a fully connected neural network looks like. And this is what a network with dropout looks like. Tell me, what do you see? Just from the picture, what are your intuitions, or what do you see over here? It should be logical. It is pretty straightforward. Just tell me, what do you see over here in the fully connected network? So Sudipto says feature reduction. Yeah, you could say that. So tell me, the number of features over here are more. Over here are more, or on the left are more, on the right one they are more. Where will you have more features? Absolutely, you'll have more features over here, right? Because it is a fully connected layer. You have fully connected network. There are so many dense connections that you see over here, right? Over here, the number of features that you are trying to do, or you're trying to look at, you are reducing them. And the hope is that so what they do essentially is, every time you feed in a new batch or a new input to this neural network, there is a probability that you'll ignore some of the hidden units, right? These units are shut down probabilistically, or no, I'm not sure what's the right term over here, but there is a probability that this unit is ignored completely. Okay, and so it's not a deterministic approach, it's a probabilistic approach over here. So let's say there is a 0.2% chance that this unit is not in the picture anymore. So what would happen is there would be no connections from this neuron to this neuron going ahead for that particular image, or for that particular training example will ignore this unit completely. So what would happen essentially is, no, for every time you're training an image, can I also say that I'm training my neural network, or I'm training on a new neural network every time? If there is a probability associated with hiding one of these units every time, is there a, can I make a statement that I am training on a completely new network, or not the exact same network every time? I'm training on a new network for every image. The architecture is also changing, I would say, right? The connections are changing. So can I make a statement that if I'm using a dropout, I'm actually training every time I pass my input signal, I'm passing through a new network every time? Can I say that? Is that a valid statement to make? That when I use a dropout, there is a probability of hiding all of these units at some point, right? So it's almost like this is out of picture. So can I say that I'm actually training on a new network every time? Is that a valid statement to make? Or do you think, no, that's not uh, true exactly? Okay, yeah, it's a valid statement to make, because every time you have kind of some nodes kind of appear, some of them disappear. So it's a new network that you're training every time. And have we seen this technique before? When we have different networks, then you superimpose them on each other. You have different models, and then the end effect that you have is a combination of different models. What is this technique called? So you have different trees, and then you combine those trees to form a ensemble of trees, right? So was this ensemble learning? Yeah. So essentially, with dropout, you are having the same effect that you would have with some sort of ensemble learning technique. Remember that I also made a statement that a neural network is just a fancy name for ensemble of logistic regression classifiers, not specifically logistic regression units, because in recent days, instead of using the sigmoid function, people have moved on to the ReLU activation, but the concept remains the same, right? So it's an ensemble of classifiers, and plus on that, you are trying to create a new classifier every time. And the end effect would be that your hope is that because you're learning with different network every time, you won't overfit. So this is the place where you're trying to move on the left over here, which is you're trying to intentionally, I would say, you're trying to produce some noise in the system, right? All the techniques in the last few years that have been developed in the deep learning and the neural network space, you could say that they have been around. How can you produce noise in your system, or so that you don't overfit, right? The thing is, your neural networks is doing really well in trying to reach to the global minima over here, or the local minima over here, for the training data. So what you want to do is you want to put some random things in your probabilistic approaches within your network, so that some network architectures are formed, and so many different things, so that eventually the hope is that you don't overfit on your test data as well. Okay, does that make sense on the intuition or the idea behind the dropout, or why it would work, on why hiding some units will actually create a new network every time? And we already seen that in ensemble learning. I also gave you an example of audience poll. Now when we spoke about ensemble learning techniques, is rather than taking advice from one expert, it's also good to take it's as equal no, it's beneficial to take an opinion from 100 people who might know a little bit more than just a random guess, right? All right. So pretty huge revision today. I guess we had a lot of things to cover, and this is the new concept that we spoke right now. But all of these things are important, and I did not want to miss out on them. Unless these things are fresh in your head, it's very difficult to grasp new things. So we'll try to see how much we can cover today. We are already a little behind on convolution neural networks, but we'll see. All right, so I'm showing you an example of how the performance gains one might get using dropout. So this is the test error rate on the benchmark MNIST dataset, which is used for digit recognition. I am sure all of you have heard of it until now. Like if you are doing this lecture, that means you would have heard of the MNIST dataset. So over here, you'd see that this is the benchmark or the state of the art without any dropout implemented, but with a dropout probability of 0.5 and 0.3 over here, these two lines, the red and the blue lines, you would see that with the number of epochs increasing, you are actually doing even better on the test data, right? So it is even better on test data with some dropout implemented. You see that there is some noise over here, right? It's not so smooth. There is a noise over here because, and you could imagine why that noise would be, because you are introducing that noise. You are randomly shutting off some units. So you don't, you're not getting a very smooth curves over here, but you'd see that overall after a certain number of epochs, you are doing better than the state of the art, performance without dropout. Okay. So this is with dropout. And over here, this is a dropout with 0.7% chance. It's like, you are like shutting off neural networks most of the times. So there is a large probability that you're shutting off all your networks. So you are essentially underfitting over here. So this is 0.7, but with 0.5 and 0.3 probabilities, these are the most common numbers that you would use. So you would use somewhere around 0.2 to 0.5 dropout probabilities in your networks going ahead. Okay, does that make sense? Is everyone with me until here? Yes, Sudipto. Dropout is a hyperparameter that we are controlling, and that's what I mentioned over here. Is these all are the hyperparameters that you control to make sure that you are not overfitting. Okay, so dropout is one of them. And if you just think that we have enough hyperparameters to work with, and there are so many experimentation that you need to do, well, welcome to the world of convolution neural networks, and you will have at least twice more hyperparameters to work with now in convolution neural networks as well. So all the hyperparameters that we saw until now, plus let's add 20 more hyperparameters, and that's convolution neural networks for you. Okay. So it's pretty crazy, and that's why I'm not so. I would say, let me just make a statement. I don't see the state of the art going ahead in like 10 years be based on something like. I would be surprised if it's very much same on deep learning or convolution neural networks. These things work in practice, no doubt, but there's so much of experimentation involved, and it just it doesn't feel right. I don't know. There are like you are tuning and you are working with like 100 different parameters, not 100, but at least 20 to 30 different hyperparameters that you're working with, and all of them you're putting them in grid search or random parameter search. It takes a lot of time to find those parameters as well, in terms of finding those hyperparameters that really work well for your system. But I'll be surprised if going ahead, we don't have any drastic changes in these architectures. And so, okay, let's come back to deep learning for large images over here. So till now we have been dealing with pretty less number of features over here, right? So when we, let's say we worked with this image over here, when we were doing SVM, we were working with this image, which was 28 cross 28 times 1, because this was one channel. It was a no, it was a grayscale image that we had thresholded, so it was only one channel over here. So the input feature size was 784 pixels that we were working with. Does everyone remember this from the SVM class when we were working with the digit recognition dataset? Yeah. So we were working with 784 features. So let's say we have 100 hidden units in our in our neural networks. Okay, so we have 100 hidden units over here. Let's say we have 784 input features over here, and in the first, I would say the first hidden layer over here, we have 100 units. Okay, so what are the total number of parameters these connections we have? So if you have 784 input features, right? So you have x1, x2, x3, and so on, and then you have 100, let's say just 100 hidden units, right? So you have 100 hidden units. So will we have 784 times 100 parameters in the first layer itself? Does everyone agree that this set of W1s over here will be 784 times 100? Yeah. So we have 784 times 100 parameters in the first layer. Okay, in the from the input layer to hidden units, right? So from input to hidden, we have 784 times 100 parameters to deal with. Okay, but for a lot of real world applications, you can't expect your images to be this small, right? This 28 by 28 pixels is a very small image. For any I would say any recognition algorithm to be sophisticated enough, in today's world we work with even like 10 megabytes or even 10 megapixels of images, right? So let's even consider this small image of 1 megapixel. I hope it's around 1 megapixel, right? Around that range. So this is 1000 cross 1000 pixels times 3. And why do we have 3? Because it's a color image, right? So I want to work with color image. I don't just want to be restricted with these grayscale images. Let's say I want to work with these color images. So how many input features do we have now? We have 1000 times 3. We have 3 million input features now. Okay, that's a lot of features, right? We have 3 million input features. And what would happen with just 100 hidden units now? Now you have 1 million times 100. It is 100 million parameters in just your first layer. And even by the modern standards, this is a lot of parameters. Okay, so yeah, my bad. This should be 3m times 100. So this is 300 million parameters in just the first layer, right? So that's a lot of parameters. Even from the modern standards, 300 million parameters is no small. Essentially, there is a high chance that you are just gonna remember all your input images with 300 million parameters. Okay, so there is if you do a fully connected layer over here, right? Just what we have been doing until now, there is a high probability that you're just gonna overfit with those 300 million parameters. Does everyone agree with me on that? That if I use 300 million parameters just for my first layer, you know that with increasing the number of parameters, and increasing the model complexity, what it does to your system, right? As you increase your model complexity, as you increase your number of parameters, this is where you will end up with. Does everyone agree that this is not such a good idea? Now, if you just feed your input image directly with so many 3 million features and 100, even just 100 hidden units, you're going to end up with 300 million parameters. The one thing is you are most likely going to overfit, and doing computations on these 300 million parameters is no cakewalk as well. It's not going to be easy to do backpropagation algorithm on 300 million parameters. Do you agree on that? It's going to be computationally tough. You're going to take forever to do this. Does that make sense? Yeah. So how can we overcome this? What can you think of? So from whatever you have learned in this machine learning career track, what is is there any technique that you could think of, or is there anything that you could think of on how can we deal with this situation? Yeah, Sudipto says feature reduction. Okay, so if some way, if this 1,000 times 1,000 was not that, because this thing increases exponentially, right? You have this 1,000 multiplied by 1,000. Now this thing is increasing exponentially. If there was some way I could reduce the number of features over here, I can make it manageable. So either you reduce features, but if you reduce features, let's say I take this 1,000 cross 1,000 image over here and I make it 28 cross 28. Can I do that? Can I make this 1,000 cross 1,000 to 28 cross 28? You can do it in your Paint or whatever image editing tool you want to use, right? What would happen over there if I do that? So guys, my question to you is, what would happen over here? So my question is, what would happen if we resize this image from 1,000 cross 1,000 to 28 cross 28? Like theoretically we could do that, right? And then just feed it to our input neural network, and it should work pretty much the same thing. But can we do that? What might happen if we reduce the size from 1,000 to 28 cross 28? What would happen if you do that in your Paint? Yeah, the size will be reduced. That is obvious, because you are reducing the number of pixels, right? You are reducing the size. And that's my question. If you put this in Paint, you go to File and crop, or you do change, resize this image, and say from 1,000 cross 1,000, you go to 28 cross 28. What would the resulting image look like? Will it look the same, or will it look blurry? Yeah, it will look blurry. And why is that happening? Because you are losing information, right? You're losing information when you did that. When you do a resizing of your image, you are reducing information, and that's why your image will look blurry over there. So reducing the number of features is one way, but we saw that if you reduce the features, there is a good chance that your image, you lose information, right? And all this time that we have spent in collecting this good quality data, now why would we want to lose information then, right? So another way to go about tackling this is what we call as feature extraction. So rather than reducing the features, right? So there is a subtle difference in these two things, okay? So either you reduce your features, or what you could also do is called as feature extraction, okay? And understand the subtle difference between these two things. What if there was some way through which I could extract some important details about this picture without having to represent them in this 1000 cross 3 times values over here? Is there a way I could extract the underlying information from this image without having to compromise on the loss of information? And that's what we try to do with feature extraction. And if you remember, when we started off with deep learning, I had told you that in olden days, what people would do is they would have some computer vision expert. Let's say you have an image of Apple over here, and you have a computer vision expert, right? A computer vision expert who would look at your input image and then extract features from it, right? So maybe you could do something like edge detection, right? So you do an edge detection. So you have just your edges over here. The information that you're trying to give about the Apple is still there. You are losing some information, yes, but the important information is not lost. The important information about the shape of the Apple is not lost when you do something like an edge detection. And then you feed it to your machine learning algorithm, and then you can get some good results. And the same thing that we are going to do over here as well. What we would like to do is take the input image over here, and somehow we would like to extract some meaningful features out of it, okay? And that's the basic idea behind convolution neural networks, okay? So this is what we would do with convolution neural networks. We would give this input image. Let's say the task is on classifying cats versus dogs, right? So you have a lot of input features, 1 million to 10 million features that you are feeding in. And you'd pass it through what we call as convolution layers. Okay, we'll see what these layers do and how do they function. But the broader idea is that you pass it through layers over here, or you want to pass it through some sort of filters which will extract the lower level features within these images, okay? And there are two concepts on why they are able to extract these many features from these images. And we'll talk slightly about going ahead about these two things. The one thing that they do is something called as feature sharing, and the other thing is sparse connections as well. Both these two things you must have we have spoken about them in some form of other, okay? Feature sharing, again, there is some spatial correlation between all these images. Do you agree that any image that you give, the neighboring pixels are somehow correlated with each other? When I draw a bounding box over here, the neighboring pixels are correlated with each other. Do you agree with me on that? That for any image, take any natural image, the images, the pixels which are adjacent to each other, they are highly correlated, right? And what if we could use this spatial correlation property of these images to do some sort of feature sharing, so that instead of having those 1 million parameters, we have a lot of parameters which are actually shared, and maybe we can reduce those number of parameters, right? So that's something that we are going to try to do. So using some sort of feature extraction technique, which we are calling it as convolution layers. We'll see how these layers function, but using them, we will downsample our 1 to 10 million features into a set of features that we can actually work with. So we'll reduce them to maybe about 1K to 10K features, or the activation units over here, which we can work with. Okay. And then we'll feed it to our fully connected neural network, and then we'll do our regular predictions like we have done until now, right? So this is something that we have already seen, the fully connected network that we have worked until now. So the new thing with convolution neural networks is this convolution layer, okay, which will help us to extract lower level features from, or important features from our images, to reduce the number of input features from, let's say, 1 million to 10 million features. We'll come down to 1K to 10K features, okay, which is now then manageable from our fully connected network. Does that make sense on the basic idea behind convolution neural networks, on how they might function? Are there any questions? This part is the same. The second part is the same over here. The thing that we have already seen until now, which was the fully connected network. You have a lot of neurons which are fully connected with each other, and universal approximation theorem told us that even with one hidden layer, you could do as many, you could approximate any function. But people have moved towards, rather than building shallow networks, we have moved towards making deeper networks, because the properties that they have. On the input side over here, we are doing something interesting. We are taking this input image and passing it through what we call as convolution layers. We'll see what these convolution layers look like. But the hope is that, the goal is that passing them through this convolution layers, we'll be able to extract important information. We will be able to extract important features and still be able to reduce the number of features over here, right? So we are just taking most important features out of these images. Okay. Does that make sense? Is the high level idea clear on what is the goal of these convolution layers? Because now we'll be zooming in on what happens in this layer over here. But before that, I want you to understand the bigger picture. Does everyone understand what happens in part 1 and what happens in part 2? Are there any questions? Okay, all right. So let's see how convolution layers actually operate, and how are they able to actually extract some meaningful information from an image. Okay. So over here, I'm giving you an example of an image. So think of this as a grayscale image with the values which are given in the grid cells over here. Okay. And I have shaded these cells based on the intensity of that, the number over here. So the 0 over here is a bit darker, is a bit on the darker side. And the 10, as you would know, is like, you would go from 0 to 255 levels of gray, right? So 255, consider this is the brightest one. So this will be the most white. So think of it as going from darker areas to a bit more brighter areas. So you have this simple image over here, which is now all 10s on one side and all 0s on the other side. So this is what, this is what the image looks like. And these are the values of those image. And we are dealing with a very small image over here, like a 6x6 image, right? But the concept remains the same for whether it's a 6x6 or whether it's a 6x6 or whether it's a 1 megabyte or 1 megapixel cross 1 megapixel. Okay. So first tell me you understand what is this matrix over here? This matrix over here is an image. The values of each pixel are given in this cell over here. The shaded area on that cell denotes the intensity of that cell. right? So the 0 is on the darker side, 255 is on the brightest side. So 10 is a little bit more brighter than 0. Does everyone understand what this matrix denotes? So just by looking at this image over here, can you tell me? Yeah, sure. So here's what this table over here is. Okay, it's an image. Okay, it's an image. It's a grayscale image. Okay, it's a grayscale image of size 6 cross 6 pixels. You have 1, 2, 3, 4, 5, 6 and 1, 2, 3, 4, 5, 6 pixels. Right, so it's a 6 cross 6 pixel grayscale image. Each pixel over here has, I'm denoting the number over here, which is the intensity of that pixel. Okay, so this pixel has an intensity of 10. This has an intensity of 0. Okay, so the 0 is a bit darker and 10 is a bit brighter than that. Is that clear now? What this is a very simple image, which is a very small one, and these are the intensity values of that pixel, of that image on that image. Okay. So just by looking at the image, can you tell me what kind of feature over here is present in this image? Is there a feature? Is there a feature that you think is present in this image over here, in this very simple image? Is there a feature that exists? Or let me put it this way. Can you see an edge on this small image over here? Is there an edge which exists? Is there an edge over here? And where is this edge? So imagine that you are zooming in. There is a big image. You're zoomed in to a very small section of that image. And that's why you're seeing a small 6 by 6 area of that image. And you see something like this over here. Do you think there is an edge which is present over here? Yeah, the edge is present right over here. You see? On one side, you have darker images, darker pixels. The other side, you have lighter pixels. You have an edge in this image right over here. Does that make sense? You are zooming in to a big section of an image and you saw these intensities of gray levels. Can I say that there is an edge which is present in this section of that image? Do you agree on that? So our task is, let's say we want to find this feature, right? We want to find this edge in this image. And now, how do we go about finding this image or this edge, this feature over here, right? You have a lot of pixels, you have 36 pixels over here. I'm interested, the only information that I'm getting from these 36 pixel is that there is an edge. Okay, that is the only information that this 36 pixel is conveying. If you want to summarize in English what these 36 pixels are telling you is there is an edge right in middle. Okay, and if there was somehow we could do this mathematically over here and tell it to our neural network, no, our task is done. So this is our task. We want to take this 36 cross 36, 6 cross 6, 36 pixels and somehow detect an edge which is located right in middle over here. Okay, and let's see how we can do this using convolution. So what you would do is multiply, or no, not multiply, do a convolution operation within from this image to what we call something called as a filter over here. Okay, so this is a convolution filter. Essentially what you do is, let's say you have a filter like this. This filter is essentially also a matrix. Okay, so you have a matrix, 3x3 matrix. Now some people call it mask as well, some people call it filter. Generally you would see in deep learning world people refer them as filters. When you talk in image processing world, people call them masks. Okay, so let's say this is a 3x3 filter over here. When you do a convolution operation with this entire image, now this is how you should go about doing it. So what you would do is essentially superimpose this grid on top of this image over here. So imagine that you are moving this, sliding this 3x3 filter throughout this image. So first you place at the top left corner over here, and then this result R1 will be nothing but summation of multiplications of these all values. So this will be 10 times 1. So this is 10 times 1 plus this 10 times 0 plus this 10 times minus 1, and so on. You do it for all these values, for all the respective values. Okay, so you do this for all the values and you add all those values up to get the first pixel in your result operation, which is R1. Okay, does everyone understand how the convolution operator works? It's essentially a dot product. Okay, so imagine you have two matrices, 3x3. You want to take a dot product of these two matrices. All you do is 10 times 1 plus 10 times 0 plus 10 times minus 1 plus this 10 times. So all the respective values are multiplied to each other and then added, all the results are added then. Okay, can you tell me what should be the value of R1? What will be the value of R1 if I do that? So multiply each respective values of the filter with that of the image and then add all the values together. It should be pretty straightforward. You can just do it in your head. You don't even have to put it on paper. It is pretty simple. Just look at it because of the way the images are laid out. Can you tell me what will be the value of R1? Or let me know if you want me to repeat on how the convolution operator works. All right, so again, it's pretty simple over here. Let me do this. So imagine that this grid over here, this 3x3 grid is placed on top of this cell over here. Okay, so once this is placed on top of it, let's say if I put these numbers over here, I say 1 is over here, this is 0, this is minus 1, this is 1 again, this is 1, this is 0, 0, and minus 1, minus 1. Okay, so imagine that all these numbers are placed on top of over here. So all you do is multiply these two things together. Okay, so multiply 10 times 0, 10 times minus 1, 1 times 10, multiply all these cells that I have put something like a superscript over here, and then add all the values up together to get one value. Okay, and can you tell me now what will be the value of R1? So multiply 1 times 10, 0 times 10, minus 1 times 10, all of these, and then add all the results together. So what will we get in R1? And you don't have to do it manually. So look over here. So when you multiply all these ones together with tens, right? In this entire column, you'll get all tens, 10 plus 10 plus 10. Is that correct? When you multiply all these zeros with all these tens, you will get all zeros. Is that correct? And when you multiply all these minus ones, right? So when you multiply all these minus ones with 10, you get all minus tens. Is that correct? So essentially everything will cancel out. So this is 0 and these 3 tens will cancel out with these 3 tens. So you will get R1 as 0. Tell me if you agree. Okay, so let's do something similar for R2 now, wherein let's say if you slide this window by one position on the right. Okay, so I'm sliding it along the x-axis little. You see, I'm just taking the filter and sliding it along the image on the right. Now, can you tell me what will be R2? Yeah, it will be 30, right? Because all these zeros are gone. So all these tens are gone and minus ones are gone because all these are zeros and you are left with all these tens. So 10 plus 10 plus 10 will give you 30, right? So you get 30 over here. Correct? So let's say if you do it for the entire image, you would get something like this now. Okay, I've just filled it out, the same operation, just slide it off, slide this. So imagine you have this. Imagine you slide this filter along the entire image. So you take it like this, then you'd come over here, then this is the second value, this is the third value. And once you reach the bottom of that image, you move one block downwards. Okay, so you slide it from here, then over here, then here, and here, and so on through the entire image. If you slide it through the entire image, you'd get a 4x4 matrix with these values. Is that correct? Can you just look at it and verify it for me that you would get this 4x4 matrix with this convolution operation? Yeah. And if let's say if I color it out again, just like I did for the first slide, I'm just coloring it off with the respective intensity values. So zeros I'm colored with a particular color, 30s this is even more bright than 10, right? And so on. So can you see that this edge which was present over here, we have been able to detect it in this 4x4 matrix. We are like shouting out loud to our neural network. Is the only message that we are giving is that, hey, there is an edge. Do you agree with me on that? That with this matrix over here, this is what we are shouting out to our neural network, or no, this is the result of our operation, is that we are saying that, hey, look over here, this is 30, 30, 30, or no, there is an edge. And can you think, why is this happening? Why are we getting all these 30, 30s over here? Or how are we able to detect this edge over here? So first tell me you agree that no, seeing all the 30s over here, and because I've colored it now, so it is much more easier for you to tell that, hey, yes, we are detecting an edge over here. So first tell me if you agree with that, and then say why is this happening? Like, no, what are the reasons we are getting 30-30s over here? Like, what is the trick that we are doing? So the trick that we are doing over here is selecting the right numbers over here. Do you agree with me on that? If we are selecting the right numbers in the filter parameters, the pattern that we have used over here is doing all the trick. The pattern of 1 0 0 minus 1, okay, this pattern is doing all the magic over here, and because of that we are able to highlight this segment of the image which which has an edge over here. Do you agree with me on that? The numbers that we have selected carefully over here, the 1 0 minus 1, and the pattern over here is doing all the trick. So if you look carefully over here, now let me also correlate this with something that you might have studied in your signal processing class. So now this is nothing but also a high pass filter. Okay. What this high pass filter is doing is whenever there is an abrupt change in your image, no, it is giving high values to those regions. When you have your image pixels which are not changing, in this region the pixels were not changing, there were all tens over here, right? So what does a high pass filter do when your signal is stable? Your high pass filter doesn't have any output, and the output is 0. But as soon as there was an abrupt change in your input, when your signal went high, your high pass filter output also went high. Is that correct? So this is your high pass filter result. So this is what we are doing for edge detection. Similarly, we can't only detect edge, we can detect more patterns and more features in our image based on the number that we select using the convolution operator. Is that clear? Or does that make sense? So one thing that you would have noticed over here is there are two things that we are doing. The first is obviously that we are detecting the edge. What is the other thing that you have noticed over here? So look at the size of the inputs and the size of the output. How many features were there in the input? 36. And what is the result of the convolution now? Because the way you slide this window over here, right, you would have less number of positions where your 3x3 matrix can fit over here, right? Your 3x3 matrix can fit over here. This is one position, then the second position. Sorry, this is not a 3x3. So 1, 2, and 3. Right, so there will be 4 positions where you fit in 1, 2, 3, and 4. Okay, so there is this 4 positions where your matrix can fit on this image, and that's why you have a 4x4 matrix over here, right? So what is the other thing that are happening? That one, that you are detecting the edge, but the number of features or the number of parameters in your output model, are they also decreasing now? Do you agree with me on that? And that's what we started off with, right? That's the reason of, we wanted a convolution layer. As I said, we have a lot of input features. If we want to reduce the number of features, we want to do an operation which can give us the same information. The information is still preserved, that there is an edge, but we are doing it with less number of features now. Does that make sense now why this is so useful? We are still detecting that there is a feature present, but we are doing it with less number of pixels now. Okay. So there is one good thing about convolution, that no, it reduces the number of features as such. But if the output image size starts decreasing a lot, that it might be a challenge for us, right? Let's say we have a deep neural network with a lot of layers, a lot of convolution layers, right? That's how people generally use these layers, is one convolution layer next to another. So we'll see that going ahead as well. But let's say if we do that a lot, if we have even a significantly large 1 megapixel input image as well, going down the network with 50 layers, this might become like really tiny. This might become like 10 cross 10 image, right? And that's not something that we want, because then again, you have challenges with the information loss and so on, the activation, you have the degrading gradient and so on, right? So to avoid that, what we also do is we want the size of the image to still stay the same. Okay, so irrespective, we detected the edge, that is good. So edge detected. That is good, but going down the network, we might reduce the size a lot. So what we do is something called as padding. Okay, and with padding, what we do is, and also one thing that you note over here is these corner pixels. When you slide this convolution filter through the corners of the images, you would notice that these pixels are considered less number of times, because when you place this filter over here, 1, 2, 3, the result of this entire thing is this pixel. So these corner pixels are considered less number of times, whereas these pixels in the center, now they are considered more number of times, right? So this filter will also consider it, this filter will also consider it, and so on. So to avoid any loss from the corner pixels as well, if there is some information in the edges of the image, what we like to do is also pad that image with some zeros over here, right? So what if we pad the input image with a lot of zeros? Okay, and now then do the convolution. Okay, so what that would do is the corner pixels are also part of the convolution many different times, rather than just doing it once or twice. Okay, so that way what you see over here is the input image size. Let me draw it properly. So the input image size, if you notice over here, is same as the output image size now, right? So the input image size is the same now with the convolution, with the padded convolution now. So that is something that we like to do, is we pad. Now there are different techniques on what kind of padding you could use. So when you say valid padding, that means you're actually not doing any padding. When you say same padding, which means you want the output size to be same as the input size. Okay, and what you could do in padding is also different options you have. You could either fill it with zeros, okay, and that's normally the convention, or you could just duplicate these border pixels as well. You just copy these pixels all over here. Okay, does that make sense on why would we need some padding? Is one, because of the corner pixels, they are considered only less number of times if we don't do padding, and the other is also the activation size will go on reducing. If you have like 50 layer in deep neural network, then your with convolutions, no, your image size will start reducing a lot. Does that make sense on why would we do padding? Okay. So here's a quick formula over here to, if you want to calculate the output result size of the convolution operation over here. So let's say if you have a 6x6 image over here, and again tomorrow we'll do a example on this, so don't worry a lot, but just make sure that I want to make sure that I put it out over here. There are some terminologies that let me introduce over here, the terms over here. The F is the filter size, and this is a K/F over here. So this is all the F, the convolution kernel size. The input image size is N in, N out, and the padding, which I just spoke about. Let's say if you do one padding over here, right? So you are doing one row of padding throughout this image, and the result size will be given by N out, will be given by N in, which is, let's say if you have 6x6 image, so 6 plus over here we have two border pixels, right? So you have one pixel over here, one pixel over here. So you have 2 pixels. So 8 minus the filter size. So the filter size is 3 over here, by the stride size. Now what is the stride over here? The stride is the amount by which you are moving the filter every time. Okay. So in my example that I gave, I was moving the filter once by 1 pixel every time. Now you could move that filter by 2 pixels as well every time. So that will be divided over here and plus 1. Okay. So if you do the math, you would get the output in this case should be 6 plus 2, which will be 8, minus 3 is 5, by 2 is 1.5. And then you now just round it up. So 3 plus 1 will give us 4. So this will be a 4x4 image, which will be the output. Does that make sense? We'll do a solved example going ahead. So if the input is 6x6 with these parameters, you get a 4x4 result. Okay, that's what you are showing over here. This is a 4x4. I guess this is a 3x3 over here actually. So this is a 3x3. Yeah, so this is 5 divided by 2, which will be 2.5, and you treat it as 2 then, and then you 2 plus 1 will be 3. So this will be a 3x3 image. Okay. Does that make sense? And again, there is no rocket science to this formula over here. If you look at it carefully, what it is doing is just coming up with, if you move this filter around, you will notice the same pattern. Right? So if you move this filter around through this thing, because there are only that many locations where this filter would fit on that image. Right? So it will fit once. Then if your stride is 2, then it will fit, no, it will skip 2 pixels and then go ahead. So it will fit 3 times on this image. That's why you get a 3x3. And generally the filter size is also kept odd normally. So you'll see filter sizes of 3x3, 5x5, which are more common. Theoretically, you could use a 2x2 filter as well. But generally people would prefer an odd numbered filter, because when you're padding, that would assure that you could pad it both sides of the image. Right? So if your filter size is 3x3, you can pad on both sides of the image. And also people like to, in computer vision, they would like to have this central element over here, right? Because this is the actual, the focus point. When you're doing any kernel operations, people like to have the central focus point over here. And that's why, generally, if you have a even filter, then there is no central point as such. But with a 3x3, 5x5 image, you have a central unit over here. Okay, so generally filter by conventions are odd no odd size. Does that make sense? We'll do an example tomorrow of this entire thing so that it is more clear. But I just wanted to explain you some terminologies around the stride size and the padding size. Okay. So what happens with color images? Well, if you have color images, now you're dealing with the volume. So you do the same thing again with 3 different filters now. Okay. So you have the same filter, but with 3 different channels. So you have 3 channels now, because there are different terminologies that we are going to use. So let's stay consistent. So you have 3 channels over here. So in your filter as well, you'll have 3 channels, and you'll just add all the results of the 3 channels to get 1 pixel in your result. Look at it and tell me if it makes sense. So what would happen with color images? So note that your result right now still doesn't have multiple channels. Your result only has 1 channel right now. Okay, because you are adding all those values up also to get just 1 result. So your 3 channels 6 cross 3 is now converted to just 4 cross 4 over here. Okay, does that make sense? Have a look at it and tell me if it makes sense. So yes, the color information is not kind of lost as such, because what we'll do is, you could have different intensities for different filters over here, right? So you could have different parameters for these different filters. Okay, so depending on what is there in the color, this values will change then. Okay, so definitely we are trying to reduce the number of so again, there is a trade-off over there, right? We want to preserve as much information as we can, but we want to keep only the important stuff. So that's the reason over here, that yes, the individual, we won't be able to make out the differences between what is happening in the red channel, what is happening in the green channel, what is happening in blue channel, but we'll just quantify whatever is happening in this region with 1 number. So this 2 is neither of RGB, it is a combination of all these 3. So it is this plus this plus this. So it is, that's what I said, that the result only has 1 channel now, which is interesting. Okay. This is a sum of all the 3. So it will be exactly this. This is how we are visualizing it. It will be a 2D matrix. This will be a 2-dimensional matrix. There is no depth over here. It will be flat. If you have this 3D, the filters are also 3D, but this will be 2D. It will be flat. Yeah, I mean, if you visualize it, depending upon how you want to visualize it, if you visualize it as a grayscale, you will see a grayscale image, right? But these pixels won't mean exactly the same thing as your input image. So you might see something which is like an abstract feature. If you remember, when we are doing neural networks for the first time, I had shown you of the visualizations of some weight vectors over here, which look like some abstract kind of things, right? Now, if you do abstract art, the kind of features that you would see, that's what you would see over here. Does that make sense? So they won't be like real things. Okay, so they are not like one-to-one mapping of what existed in the real world. So there isn't a scale as such as well for this the number over here, right? Depending upon the weighted combination of these three things, when each of these things are ranging from 0 to 255, not necessarily this is ranging from 0 to 255 as well. Does that make sense? So there is, you can't say that this is a grayscale image or is a color image. These are just numbers now. If you plot it as a grayscale, you'll see it in grayscale. Okay. There will be some visual aspects for sure because they are derived from the real image, but they are right now, they are just numbers for us. Okay. Right. So this is how you do it with color images. But let's say this filter that we made over here, what was the filter that we made? Let's say we had this 1 0 1 1 0 minus 1 minus 1 minus 1, right? So what was this feature detecting? What were we detecting using this kernel over here, or this filter over here? Edge. And specifically, what kind of edge? Were we detecting vertical edge? Is that correct? Only when we had vertical edge, we would get a high response from our filter, from our high pass filter. Is that correct? When you have a standing edge, yeah. But no, that's just one feature. What if we have multiple features that we want to detect, right? So there are so many different features that could exist in an image. So in that case, what we would do is do convolution with multiple filters. So that will be filter 1, that would give us output 1. We'll have filter 2. Now this is now detecting something else. Right now, it might be detecting some kind of horizontal feature over here. We don't know exactly what this feature is, but most likely it is detecting something which is horizontal and which has high abrupt changes in this direction, right? So that would give us output 2, and then you stack all these outputs together, and now you have multiple channels in your output as well. Okay, so these are channels. So have a look at it and let me know if that makes sense now. So essentially what we will do is we'll want to have a lot of different filters, a lot of different features over here, right? And we'll stack all the outputs of all the convolutions together to get multiple channels in our output as well. So now this is 4 cross 4 cross 2. Now see, this is still better than 6 cross 6 cross 3, right? So this was 36 times 3, and this is just 16 times 2, right? Which is almost only 32, right? So we are still getting less number of features, but we have been, if these filters are doing good, we have been able to detect the patterns which existed in these image. Tell me if that makes sense to you, or if there is something not clear, please let me know. All right, so this is how we use multiple filters. And yeah, so Sudipto says, now how can we decide what filters to use? And if this was like 1990s, we would have debated on the selection of these numbers, right? So we would say, okay, no, 1 minus 1 or 10 minus 10 works much better. That was the discussion in 1990s. But what people have realized is, rather than trying to hard code these numbers, there is something that we have already seen on how to work with these things. So let me just give you some examples of other filters as well. So different filter parameters will have different effects. So if you do convolution of filter like this on this image, you would get this kind of output, right? So assuming that there is some padding over there and those things, you are detecting this kind of edges. With a filter like this on this image, you would get something like this now, okay, which is interesting again. So again, this is detecting some edges over here. This is also detecting some edges. Depending on the type of filter, we are detecting different kind of features in our input image, right? So one central concept that we could use is, rather than trying to hard code these weights, what if we learn these weights? And that's what the purpose of neural networks is, right? We don't want to hard code the features, right? What if we could learn them? So rather than treating these numbers as the number that we put in the system, what if we create a vector out of them? So again, this is W1 now, and this is the input feature X, and this gets convolved with this, right? So this is X1 times W1 plus X2 times W2, and so on, and we get some output Y, and then we do a back propagation on it, just like we did before. Is that possible now? Now this is no different than what we were doing with the linear regression models or the neural networks logistic regression model, right? Now if we consider them just as numbers that we want to learn, we can still use gradient descent and still learn these two numbers, all these numbers. And that's the magic behind or convolution neural networks. This central idea that instead of hard coding these numbers, we'll learn these numbers as well. And because of that, these networks have been able to learn parameters and these features which we as humans would not come intuitively to us. So maybe your network might learn to detect edges which are at 36 degrees. Your network might detect edges which are at 45-degree angles, and so many different things, right? Because once you let the gradient descent do its job, you will see how powerful it can get, and we have already seen how powerful it is. So rather than trying to come up with these numbers by ourselves, what we actually do is put them as an optimization algorithm, as an optimization objective in our algorithms. Okay, so that's the central idea, is that you don't actually hard code these numbers. We learn them using back propagation algorithm and the other gradient descent, stochastic gradient descent algorithm that we have seen. So this is what one layer of convolution would look like end to end. You have a 6x6x3 image. You have different filters. Okay, these weights we don't know. We put them as a weight vectors W1, W2, right? And let's say you got 3x3 output from these two. You stack them together. Then we pass them through the ReLU activation. Now again, ReLU activation is something that we have already seen. And you add a bias term and you get an output. Okay, now this should look familiar to you because this is same as what we have seen before. This is ReLU plus W times X plus B, and that is Y cap. So this is what one layer of convolution would look like. So we have gone down from 6x6x3 to 3x3x2 with two features over here, two feature vectors over here, W1 and W2, that we would actually learn using back propagation. Does that make sense? So this is good, but is there something else we could do as well? So what people thought is, when we were doing this over here, right, there is still some redundancy in terms of the numbers that we are producing, right? The whole purpose of this 30, 30, 30 is just to say that, hey, I got something over here, right? To say that these neurons, my feature is activated. I got something. This is what this is trying to do. This 30, 30, 30 is trying to say that I got something in this patch. I got an edge, right? This is what the central idea is. So can we still reduce these numbers even more? And that's what pooling does. What pooling does is it looks at this patch that was generated before and then just takes one number out of this patch. Okay, so when you got a filter size, when you have a filter output like this, what there are several approaches to pooling. You could do max pooling. You could take average pooling. Okay, or you could also do min pooling as well, but no, theoretically you could do that, but generally you are trying to get when with ReLU over here, you're trying to get large numbers for inputs which have been activated, right? So what you could do is just say, instead of saying 31117, all you could just say is just put a filter over here and just say take 7 out of it. Okay, so over here you could move that filter and say 2436, and then you could say hey, the maximum activation in this area is 6. Okay, and 9 from down below over here, and in this region the maximum activation is 3, so you take this. Okay, so you reduce the number of the features even more, or the activation size even more. Okay, does that make sense on why would we add a pooling layer? Because the intent is to get the word out. Okay, is to say I got something in this patch of the image, right? And whether I got something or not, I can just take the maximum number over here and just pass it to the next layer. Okay, this means the same thing over here. For me as an image or a feature, this two things kind of mean the same thing, but I'm just using less number there now. Okay, all I want to say to the next layer over there, hey, I got something in this and how much I got it, right? So I got something in this patch of the image. So I got 9 over here. I got 3 over here. And obviously there is some loss of information, but the purpose, as you see, now if you understand properly, is you're trying to tell, pass this information from one layer to next is what did I get in the previous layer. I'm saying that I got a high intensity in this region. This is what I'm trying to say. So I'll just pass that to the next layer rather than giving all the other 3 numbers as well. Okay. So if you put all these things together, this is what the CNN architecture would look like. So you would have a lot of convolution layers. So convolution layer 1, con 1, 2, 3, 4, and so on. As you see, the height and the width of your input will start on decreasing as you move deeper into the network, right? So if you start off with 1 megapixel cross 1 megapixel image, maybe over here you would end up with something like maybe something like 10K total features, right? And that was the intent, that you want to reduce the height and the width of your convolution layers, right? So and the other thing to note over here is generally the volume of these boxes would increase in this direction. So you would have more wider boxes over here, which is you will have more channels over here, right? So the channels are nothing but the number of filters which are present. So generally people would start off with, let's say 32 filters over here, 32 filters, 64 filters, 128 filters, and so on. Okay, as they move deeper into the network. So the boxes will become, if you want to visualize it, the boxes will become bigger but smaller, right? So as you move deeper in the network, and then you have a fully connected network just like you have before, and then you do your output using your softmax, or what we call as a sigmoid activation. Okay, does that make sense? And here's an example of a convolution neural network. This would be the last thing that we'll be covering today. I know that we had to cover a lot of theory part. I was hoping to implement the convolution part as well, but we'll do it tomorrow. So here's an example of a convolution neural net. It's a popular network which was first introduced in 1998. So it's not a new idea as such. Okay, it's a relatively mature concept. The only thing is people did not take it so much seriously because the number of layers and the hyperparameters that were involved in this technique, right? So in this LeNet 5, which is a classic example of a neural network, they had, the task was digit recognition. They wanted to recognize digits. They had a 32 times 1 channel grayscale image that they were feeding to a convolution neural network. So they had a first filter, which had 5 cross 5 filter that would get down the dimension from 32 cross 32 to 28 times 28 times 6 over here. The 6 is the number of filters that they might have, right? So now the volume has increased in this direction. So this is now 6. We have 6 channels now. Again, you do with a filter size of 2 over here. They're using a filter size of 2 for average pooling. So this 28 cross 28. So if you look over here, what your pooling is doing is, it's essentially, if you have your f equals to 2 and s equals to 2, which means your filter size is 2, and every time you move by 2 pixels, right? So you shrink your image by factor of 2 then, right? So if this was 4 cross 4 image, now this is 2 cross 2 image. With pooling layer, you'll essentially reduce it to half if your stride size is 2, right? So this is what they are doing over here as well. With 28 cross 28, with f equals to s equals to 2, they shrunk the size to 14 cross 14 cross 6. Now they applied to another convolution layer with again a filter size of 5 cross 5 and s equals to 1. That would reduce that dimensions even more. And now they would have more, I would say they would have added more 10 filters, I guess. So now they would have 16 channels now. And now so on until they have a fully connected layer. Over here now they have 5 cross 5 cross 16, which is 25, 16 5s are 80 times 5, which is 400. They have reduced 32 cross 32 cross 1 to 400 inputs over here. Okay, so I wouldn't say that much of, I would say some order of magnitude of improvements in using the convolution layers, right? So they have now 400 inputs which they give to fully connected neural networks, and then they are getting the output. So overall, they would have 60,000 parameters that they were learning in their system. Okay, and most of the parameters you would see is in this region, right? Because over here, let's say how many parameters, we'll do an example tomorrow on calculating the number of parameters, but you'd see that there are about 60,000 parameters in the network that they are learning. Okay, so I hope that was helpful on understanding CNN as a broader concept. Tomorrow we'll dive into a lot of more details in understanding, also implement that in a Google Colab. So no, they are not choosing 120 over here. They are saying that there are 120 hidden units over here. So there are 84 hidden units over here. Okay, so they are not choosing. They have all the units which are connected, but there are 400 inputs which are fed to 120 input units over here. Okay, or 120 hidden units over there. All right. Okay, great. So hopefully that was helpful. Tomorrow we'll be going over much more details in convolution neural networks and implement them in Google Colab as well. Let me know if you have any other questions. Otherwise, feel free to drop off. I'll see you next time tomorrow. Yep, goodbye.